welcome back to another video of Math Times Cool. In this video, I will be explaining a few ICANNs in the similarity unit. So I can explain how figures are similar using the definition. Well, the definition of similarity is basically same shape but not size. So as you know from my previous videos, you know that the sides are proportionate. So not the same shape, or same shape, sorry. They're the same shape for like square or something. They have the same properties, but not size. So there's a ratio between the sides. Okay. So I can use similarity transformations to prove triangles are similar. Well, if you can use all types of I can use similarity transformations to prove triangles are similar. As long as you can map one shape onto another shape using dilation, then you're fine. So let's say, let's open this up. Let me quickly get my pen. Okay, so let's say you had a shape, like let's say you had that random shape and this random shape. As long as you can dilate this shape to map let's name them. So let's say this is, oops, sorry. Okay, so let's say this triangle. As long as you can dilate this triangle to get this triangle. So let's say you translated it, right? So the triangle's like that, and then as long as you can dilate it to map it onto that other shape, then they're similar. If you use all rigid transformation, then they would be congruent, sorry. They'd be congruent since you're using rigid transformation. If you use a dilation, then they would be similar, but if you use a vertical stretch, they would be neither congruent nor similar. Okay. I can prove theorems about similar triangles. So theorems including a line parallel to one side of a triangle divides the other to proportionate and conversely. The Pythagorean theorem proved using triangle similarity. So how about we do, I think I'll just have this as like an entirely different video on its own. So we will come back to that and do that. Okay, so let's move on. So let me highlight that in blue so I know to come back. Okay, so use congruency and similarity criteria for triangles to solve problems and to prove relationships in geometric figures. I can use similarity to solve problems. I can use similarity to prove relationships in geometric figures. So let's say you had this triangle, right? And you had another triangle inside of it. Actually, let me make this neater. So let's say you had this triangle, and then you had another triangle inside of it. Let's say you were told that this line is parallel to this line, and this with that. Well, okay, wait. Let's just say say that. Okay, even though they're not. Okay, let me just rewrite this because that doesn't make any sense. Because they wouldn't be parallel because they're on the same line. So let's say you said that. Let's say we're told that this line is parallel to that line. See? Okay. So now we can prove that they're similar because number one, they share that one side, so the reflexive property, and then these angles are congruent with these angles because alternate interior angles, corresponding angles of parallel lines are congruent because these are corresponding. Yeah, my drawings are not that neat, but they are corresponding. See? Okay. So now that we have that, let's do a few problems. So let's say you're told that this length is 4, and let's just say that's given as x. So you're told that this length is 4, and this length is I don't know. Let's say like 4. Okay. Yeah. Let's say it's 4. So how would you determine this whole length? Actually, how would you determine x? Let's start off with that. Okay, so again, we have these two triangles, right? We know that they're similar, so there's a relationship between this side and this side. So we know that this side is 4, and we know that this side is x plus 4, because this is x, and then plus 4, you get the whole length. So x plus 4 over 4 is equal to, and then we know that this is 2, and that this is 6, right? So we can do 6 over 2. This is 3, right? Right? And then 4 times 3 is 12. So we get x plus 4 is equal to 12. 12 minus 4. Hopefully you know that is 8. Bang. We figured it out. We know that x is equal to 8. And then we can say that this whole length is 12. Pretty simple, right? Yeah, similarity problems aren't really that hard. Let's do one more. Okay, so let's say told that these lines are parallel. I don't know. Okay, let's say that this point is 4. This point is x. This point is. No, let's just say it's 4. No, that's too easy. Let's say it's hypothetically. Let's say that's. No, let's say this is 3. This is 6, right? So, again, we have the two triangles. Whoops, why isn't mine? Okay, my marker wasn't working for a second. Okay, so again, we have these two triangles, that, and then the whole thing. So now this side is 4 right there. Now this side is x plus 4 because it's the whole thing. So again, x plus 4 over 4 is equal to, and then we know that this is 6 and that this is 3. So 6 over 3, that is 2. 2 times 4 is 8. X plus 4 is equal to 8, and then hopefully you know that x is equal to 4. So that's 4. So we know that x is 4, and the whole length is 8. Yeah, pretty simple, right? I can identify the point on a direct line segment that partitions a segment into a given ratio. I think I will do that 2 videos from now. Yeah, I'll do that. So I'll do the I can prove theorems about similar triangles first, and then this. So stay tuned. So, sorry for not uploading any geometry videos in the past, like, how many days has it been? Like, past couple of days. I've been kind of busy, but you know, I will start uploading a lot of geometry videos. Yeah, I uploaded, like, you know, the video, a video, like, you know, like, stop wasting your summer, because, yeah, stop wasting your summer. Okay, thank you for watching this video, and bye.